Okay. So next gas law I'm going to talk about is called Charles' law. Charles' law is another one of these sort of better one, better two, where we're holding everything constant, but we're comparing two variables. So Charles' law is going to allow volume and temperature to change while holding moles and pressure constant. So I think one of the best ways to think about this is thinking about a balloon. Now this is named after Jacques Charles, French scientist. So if we think about a balloon as we heat it, I think this is the best way to think about it. Because a balloon has to have, assuming the external pressure is the same, right, then the internal pressure is going to stay at 1 atmosphere, right, on the inside. So 1 atmosphere, all the way inside. So let's imagine, I'm going to kind of make the balloon bigger so I can draw a little bit better. Again, the pressure has to stay the same. And remember, P equals F over A. Now, as I heat up, there's gas particles in the balloon, and they're colliding with the outside of the balloon. And we're just going to say, for argument's sake, it doesn't have to be 1 atmosphere, but let's just say that internal pressure is 1 atmosphere, and so is the external pressure. So it has to be equal. The gas is going to automatically, so the balloon isn't smart enough to equalize the pressures. What's going on is, if the pressure outside is greater than the pressure inside, then the balloon will collapse because there's more force outside than inside. And if the pressure inside is greater than outside, then the balloon will expand until such time as that, isn't the case anymore. So if I take the temperature and I increase it by heating up the balloon, right? What happens to the particles inside? We have the same number of them because moles is staying constant. Temperature is a measure of kinetic energy, right? Kinetic energy is going to cause increase in the kinetic energy causes the particles to collide with the balloon with greater force, greater kinetic energy. The force goes up. Well, in order for the balloon to keep the same pressure can't change here. What has to happen to the area? It also has to go up accordingly. The balloon is going to expand, right? The balloon will expand so that the pressure on the inside stays at 1 atmosphere. So, assuming pressure and moles stay the same, as temperature goes up, volume also has to go up. So with Boyle's law, we saw that pressure and volume have an inverse relationship, but temperature and volume have what we call a direct relationship. So Charles' law says the volume of a fixed amount of gas is directly proportional to its Kelvin temperature at constant pressure. So remember, we have to be using Kelvin temperature here. This temperature has to be in Kelvin because we need it to be a measure of kinetic energy. For all the other variables in the gas law and these gas laws, it doesn't really matter what unit we use, as long as our two measures of volume are the same unit. Temperature, it really matters because Celsius has that 0 point in a really awkward spot, so Kelvin has to be used for temperature. Okay, so let's draw this out. So Charles' law is also consistent with kinetic molecular theory, as I was just explaining. So as you increase the temperature, there's more force on the walls of the container. This increases the volume. So I guess instead of thinking about it in terms of pressure equals force over area, you can think about it as the kinetic energy increases the pressure inside. So for a little while, the pressure inside is greater than 1 atmosphere, and so that makes the balloon expand, and then this temperature goes back down until it's 1 atmosphere again. Okay, so let's do this mathematically. So, whereas in Boyle's law, P and V had to be to make them constant, we had to multiply them together because they're indirectly related or inversely related. So one goes up, the other goes down. With two things that are directly related, volume and temperature, I'm going to put temperature in the denominator. Now, this may feel weird. This may feel like, oh my gosh, these look like they're inversely related. But if you think about it a little bit, so kind of think on this a bit, in order to keep this value of K the same, if I increase volume, I also have to increase temperature. They have to move together in the same direction to keep K constant. So in the same way that we got that P1V1 equals P2V2, we're going to get V1 over T1 equals V2 over T2. Now again, don't try to memorize this yet. I'm going to show you a nice, easy way to always be able to come back to this, so you don't have to worry about it too much. For the moment, I really just want you to focus on how to use these. So again, this is one of those better one, better two sorts of gas laws. Okay, so where V1 is volume of the gas at a given pressure, T1 is the temperature, Kelvin temperature of the gas. Again, I emphasize Kelvin temperature. V1 and V2 and T2 are volume and temperature under the new set of conditions. So again, initial conditions, new conditions. Okay, I'll come back to that last slide in a moment, a little bit later. Okay, so I want you, since I've already shown you how to use Boyle's law, try applying the same thing to Charles' law. Try doing these two problems, pause the video, do these problems, and then come back and I'll work through them. Okay, so in both these cases we're going to use Charles' law. V1 over T1 equals V2 over T2, right? So all I need to do is identify what I need. So I want, this is spelled out pretty simply, I want the final volume. I want V2. Okay, so sometimes with Charles' law there's a little bit of a trick with the algebra. So I want to isolate V2. This one's simple enough. I need to multiply by T2. You know, it just dawned on me that this one is actually for the next set because the pressure isn't something you can do. I apologize for letting you squirm away on that. I will get to how to do it momentarily. I'm sorry, guys. So V2 equals V1 over T1 times T2. So then simply put, we just solve for V2 equals V1 is 452 milliliters, and then T2, so here's where we go. From negative 22 to 187. So what's my T1? Should be the negative 22, right? So I can just put negative 22 down here, and then I can put 187. Is that all right? Actually, no, we can't do that, right? We have to convert these into Kelvin first. So remember, to convert Celsius into Kelvin, you add 273 degrees. So negative 22 plus 273 is 251 is our T1. And then 187 plus 273, 460 Kelvin is our T2. And now everything should work out just right because Kelvin will cancel. So I'm going to take 452 times 460 divided by 251. I get 828 milliliters, right? Because milliliters is what canceled out. One thing I want to warn you about, I want to warn you that if in any case you have to solve for, say, T2, let's say I had a one where I need to solve for T2. A very common mistake that people make is they divide by V2 on both sides and say, oh, T2 equals V1 over V2 T1. This is not the case. This is not true. Because V1 over V2 T1 actually equals 1 over T2, right? You can't just promote something up to the numerator because it's alone. So here's how I like to handle it. And there's a couple different ways to handle it. For one, you could just take the reciprocal of both sides. You could just flip both. Some people like the idea of cross-multiplying. What I am going to end up cross-multiplying, but I don't like cross-multiplying very much because I feel like it's a trick people do without understanding what it is. So I'm going to accomplish the same. I'm actually going to do what cross-multiplying does. Literally, I'm going to do all the steps, but I'm going to try to explain it a little more just so it's clearer what's actually happening. So in order to solve for T2, I need to get it in the numerator first. So my thing, how I think about these, is if I'm ever solving for something that's in the denominator, like T2, my first job, before I try to isolate it, is just get it into the numerator. That's my first job. So get it into the numerator, which I'm going to do by actually sort of, this is counterintuitive, I'm going to cancel it out. But now it appears over on the other side of the equation in the numerator, which now frees me up, oops, I'm not erasing very well, V2, which now frees me up to isolate it and leave it'll be in the numerator. So I can get rid of T1 by taking times T1 on both sides. Cancel, cancel, and dividing by V1 on both sides. Cancel, cancel. So T2 actually equals V2 T1 over V1. All right, so that's how I'd solve for that.